And welcome back once more to the third lesson in the Science and Statistics series. This one's on research design, and there's a lot to it. I know I've kind of hovered under 40 minutes for the previous two lessons, but this one might blow out a bit. I've even seen at other universities they have an entire separate unit on research design in first year psychology. So I'll try and be as efficient as possible to try and get through all this content. In fact, one of my first slides is, this is kind of what you need to know. You need to know about these various kinds of designs. You need to know about the various kinds of variables. You need to know the difference between random selection and random allocation. And finally, I'll wrap up by talking about blinding and replication. It doesn't seem like a lot, I suppose, but you need to know these things backwards and upside down. Every single question in the exam, whether it's mid-semester exam or final exam, every single question will be applying these concepts. If I give you an unknown experiment, can you, for example, unknown study, can you tell me whether it's a correlational study, quasi or true? So I know it doesn't seem like a lot, but you need to know it well. So let's get started with something which is far from science, and that is anecdotes. An anecdote is an interpreted story. It's a story of something that happened, but you know what the reason behind it is. I'll give you an example of an anecdote. This is me many years ago when I took my first little boy to Japan. That's me standing in the middle of Kyoto in winter. And he got sick. We were only there for a week and he got really sick. And we thought that he got sick because we hadn't bought a big tin of the Coles Nestle formula, whatever. We'd relied on the local Japanese formula, which, it was so brilliantly Japanese. It came in a tablet form. So it wasn't powder. You just dropped it in some hot water, stirred it. It was great. But my little baby got sick. So that's my anecdote. And in fact, we were so convinced this was the case, we actually called someone who was back in Sydney and said, can you go to Coles and get us a big tin of that baby formula? And I know it's caught on recently and people are making tens of thousands of dollars, but way back in 2010, I was one of the first people to import baby formula into Japan. He started drinking that and he was fine. Although it did take a few days for it to get there. But that's my anecdote. And parents are great at anecdotes because they think they know everything because they're not scientifically trained and they're so arrogant. So, if you're traveling overseas, make sure you bring the baby formula with you. And that's the end of my anecdote. But the more I distance myself from that experience, I realized that that's probably not even what happened. There's so many factors here. Yeah, there was a change in baby formula. Maybe it was just a change per se. Maybe it was the fact that we took a baby from a Sydney summer into a Japanese winter like that. That's not going to do wonders for your health. Maybe it was the water in Tokyo. I don't think it's fluoridated for some weird reason. Maybe it was a virus he picked up in the aeroplane. Airplanes are great for spreading virus. Who knows? So many different explanations. But that's not what an anecdote is. The person who tells the anecdote has already made up their mind what they think the explanation is. And that's the problem. If we just focus on the baby formula hypothesis, as it were, if we were to run that as an actual study, one baby's not going to cut it. I want 24 babies. I want them randomly allocated to either no change in formula, going from the Australian to the Japanese formula, or going back again. And then I want to measure how well or ill the babies were. I think I've got different facial expressions based on the outcome of the so-called experiment. That's what you would need to do to be able to tell someone what actually happened. But that's not what happens in parental anecdotes, and that's not what happens in general anecdotes. So this is why the plural of anecdote is not evidence, because even if you add up lots of these fully interpreted, highly biased stories, you're not creating anything bigger than the sum of its parts. You're just you're adding together misleading information. Often I've had students email me or come down to the lectern when we've been doing on-campus lectures and say, oh, look, I was sick, but then I did X. Changes over the years, and now I'm better. So X made me better, or even I am living proof X works. You know, in lesson 1, you went on about vitamin C, but I am living proof that, vitamin C is good for scurvy, I suppose. This is all anecdotal stuff. I am this, I saw this, therefore I have scientific evidence. No, you don't. Imagine that you're not feeling well, and as part of your therapeutic solution, you decide to wear a fish hat. Just bear with me. You decide to wear a fish hat, and then you get better. Did the fish hat make you better? Should you start promoting fish hat? I bet you knew what fish hats were before you started this lesson. Should you start promoting fish hats as a cure for, I don't know, whatever you are sick with? No, because the most likely explanation that I've got there right underneath that whacking great red arrow is time. Time made you better. Why does time make you better? Because you've got an immune system. And again, by the time our baby formula arrived from Sydney and then he felt better, it was time. He just got over whatever it was. It probably was a virus in Japan those many years ago. So fish hats? No, you haven't found any evidence for fish hats. But if you tell an anecdote saying, oh, I was feeling bad, then I wore a fish hat and then I got better, there's nothing scientific about that whatsoever. So it's not one of our scientific research designs for today. Moving on to case studies, you might think, hang on, case studies, small sample size, isn't it? It's more or less exactly the same thing, isn't it? And it's true, you're only looking at 1 or 2 people. In psychology, some of those really rare disorders like prosopagnosia and things like that, we're only dealing with sample sizes of 1 or 2 spread around the world and around history. How can we draw conclusions like that? Well, the main difference with a case study is you've got an open mind and you're writing down everything, and your story is not interpreted in this biased manner. Let me go back to this diagram I used in the first lesson and just focus on theory and evidence. With a case study, you're keeping your theory far away, your theory or your interpretation far away from the evidence, okay? And that will compel you as a scientist who genuinely, humbly wants to work out what's going on to write down everything, record everything. We don't give you a lot of training in undergraduate psychology in qualitative research. It's a pity. There's someone at postgraduate level who's skilled in qualitative research who can do training. It's mostly statistics, tests, and so on. But good qualitative research is good, is thorough, can be systematic, and can give you mountains of evidence that is not interpreted. And that's important because when you consider what an anecdote is, the theory's on top of the evidence, okay? I tell you my story about the baby formula making the baby sick and fail to mention the million other things that it could have been. That's because I'm interpreting the evidence for myself, and no one else can come back later and reinterpret it because I failed to mention so many things. But when you keep them separate, it's really, really useful. I'll give you a real life example. Cholera, terrible disease, still affects millions of people around the world in the modern world, sadly. Lots of children die from cholera in the 2020s, which is disgraceful, but it happens. And yet cholera we've known about for hundreds of years. There was a theory of disease called the miasmatic theory of disease, which basically boils down to bad smells make you sick. It's not true, of course. It was replaced with the germ theory of disease, which is viruses and bacteria tend to make you sick. But it's interesting to see how it evolved. Now imagine if we were taking our evidence for cholera in terms of anecdotes. My auntie Liz got cholera from the terrible smells and gases coming from the river near her house. So the first sentence alone is a conclusion. There's no separation of theory and evidence. It's just, this person seems to know what the answer is. She moved house. She avoids bad smells. She hasn't got cholera since. Well, there you go. And there's my anecdote. scientifically useless. Imagine if you were trained in qualitative research hundreds of years ago, you would write down everything. When winds were blowing from the east, terrible noxious gases, okay? Her house was located next to the River Thames, which at the time contained a large amount of raw sewage. They did not have a sewerage system under London. They did soon when they worked out what was going on, but they didn't at the time. And she drew her drinking water from a well. Now, if you had this complex evidence from 1723, you could then look at it through a modern lens and see, well, that red bit's irrelevant. It's not the smell. The smell is associated with it because it's associated with the presence of raw sewage. It's the bacteria that's in that sewage that's causing the problem. She's living next to the Thames and she's drinking that water. That's why she got cholera. And that's why so many people were dying of cholera. And interestingly and historically, the people in London did build one of the world's first sewerage systems based on the miasmatic theory of disease, that they were locking the smell away, but of course they were also locking the bacteria away underground, and they were saving thousands of lives as well. So that's the advantage of a case study. There's no prejudgment. Everything gets written down. And that's really kind of it in terms of qualitative research for your first year course. So I'm going to move quickly on to correlational studies. I'm going to get into some numbers. Now, for a correlational study to exist, you need at least 2 measurements per person. For example, someone's height and their IQ. And you look at the association between them. And this is something I won't return to again till the very last lesson, lesson 6. But if I were to tell you that IQ is correlated with height, it would be to say that one is associated with the other, such that taller people have higher IQs. I promise I will return to that in lesson 6. Know what a correlation means by looking at it. When you see a number in a published research paper or a research report, perhaps that you're doing, know how to interpret it. The first thing you should look at is it negative or positive? If, as one number gets bigger, the other one gets bigger, the correlation will be positive. If, as one number gets bigger, the other one gets smaller, then the correlation will be negative, as it is there. The other thing you want to look at is the value. Now, correlations don't get bigger than 1 and don't get smaller than -1. This one's a 0.7. That's quite a strong correlation. There's some guidance there. 0.1, 0.2, 0.3, it's fairly weak. 0.7, 0.8, 0.9, very, very strong. Just to give you a ballpark, the correlation between HSC performance and university performance is about 0.4 at Sydney University, which isn't too bad. It's not strong. It gives a lot of, if you didn't do that well in the HSC, there's every chance that you'll do very well at university and vice versa. Because a perfect correlation of 1 to 1 would be 1 or -1. You rarely get that. You get 0.1s, 0.5s, and so on. Let me give you some more examples. The one I just mentioned, the perfect relationship on A, that would be a correlation of 1 in the top left. And again, it doesn't matter what these variables are. There's just 2 measures: height, IQ, HSC score, university score, whatever. The one on the top right, you can see as values on one variable go up, the values on the other one kind of go down. There's a bit of a scatter there, so that would be a -0.5 correlation. The one on the bottom left, that's quite a neat relationship. You can see the line of best fit, even if it wasn't drawn for you. That's a positive 0.8. The one on the bottom right, though, if that line of best fit wasn't there, you'd have trouble seeing the relationship at all. That's a very weak positive correlation of 0.1. Now, every psychology student remembers this, even if you don't remember anything else. Correlation does not mean causation. And very, very quickly, if X correlates with Y, X could cause Y could cause X, or something else could cause both. The fact that two things are associated and one thing seems to go up when the other one's going up or going down doesn't imply a causal relationship. I'll give you some examples. Don't eat before you swim was the theory of one person who, I think they were a contributor to the 1950 Red Cross safety manual. A single GP believed that if you ate before you swam, then you'd suffer some kind of stomach cramp and you would drown. Absolute rubbish, not true, never supported, and Red Cross removed this from subsequent editions of their safety manual. Too late. I bet your great-grandmother or your grandmother and possibly even your parents, if you grew up in Australia, said, oh, wait half an hour before you swim. Jeez, see, once bullshit is out there, it's so hard to pull it back in. It's absolute rubbish. Imagine that eating ice cream correlates with drowning. Eating ice cream is X, drowning is Y. Well, it's probably not X causing Y based on what I just said. Look, if you have a heavy meal before you go swimming, you may see the meal again, but it's not going to kill you. You can eat as much as you like before you go swimming without worrying about drowning. Okay, what about the opposite? What about drowning causes ice cream to be eaten? Maybe when someone drowns at the beach, everyone's told to get out of the water. People like sticky beaking. It's getting very dark now. I don't like the example. But then more people eat ice cream as they stand around. It just seems unlikely. This example, eating ice cream is associated with drownings, was made for this bottom situation here. Z, something's causing both. What? Heat. Heat is causing both. When it's really hot, tragically in Australia, more people go swimming and more people drown. Please, if you're an international student or unfamiliar with our surf, swim between the flags and don't swim late at night or early in the morning when no one's about. Please, please, please be safe. When it's hot, more people swim, more people drown. Z causes X. And when it's hot, more ice creams are sold. When it's cold, not so many people swim, not so many people drown. When it's cold, not so many people buy ice creams. Except my 4-year-old, who can order an ice cream in winter for some bizarre reason. Must be the sugar. So you can see the correlation between X and Y is not a causal relationship at all. I'll give you another example. In winter, when it's cold, we get colds. And in fact, when you think about it, calling a cold, cold and flu cold, calling a cold is just the most self-contained anecdote you could ever imagine, that humans have come to attribute the illness with being cold so that they now blame it on the cold, when no evidence has ever shown that. Viruses cause colds. Cold doesn't cause colds. You can be in an Arctic research station, the coldest place on Earth, and the virus doesn't magically appear out of nowhere. You will catch it if on the next supply ship someone brings the virus in, but you can be as cold as you like and you're not going to spontaneously get a cold. You'll get it. Look, here, I can understand where it comes from in human history. If you go out into the cold, even if you don't have a virus, the cold does terrible things to your respiratory tract. You get a runny nose, you get sore throat and so on. But the moment you go inside and get warm again, you can get rid of all those symptoms. So it's similar to the virus, but yeah. So at any rate, cold doesn't cause colds. X doesn't cause Y. Certainly you can't have here Y causing X because, viruses can't cause the climate to be cold. Again, it's that third variable that's causing both. And what is it? Why do we get more colds and flus when it's cold? Because we close the windows, because we stay inside. Z is temperature. Once again, it's the same friggin' variable. Staying inside. Oh, sorry, it's a little more complex. Cold weather causes us to stay inside, and then we get more colds. Okay, this is the worry about COVID during winter and COVID in enclosed spaces, which is why we need to be opening windows, we need to have air circulating and so on. There's a website, I need to tell you about this, otherwise 50 people are going to email it to me anyway. I know about it. There's the link there in the bottom right. And This is the most sensible correlation I can find on the website, and it makes sense. Money spent on movie theatre admission and amount of rainfall in Pennsylvania. They track each other quite closely. You can see the correlation there is 0.53, okay? That's the only one I found that wasn't silly. But what the website does is is clearly demonstrate that just because things are correlated with each other doesn't mean one causes the other. I think this is plausible. Yeah, when it's raining, you've got nothing better to do, you go and see the movies. But what about this one? Number of people who drown by falling into a swimming pool, highly correlated, 0.66, with number of films Nicolas Cage appeared in. Or this one, divorce rate in Maine and per capita consumption of margarine. That's a correlation of 0.99. Someone's been looking for that. That's not causal, but it's hilariously close. Margarine, divorce rate, you mine enough data, it's amazing what you can find. So let's go back to the person being sick and wearing the fish hat. This is really just a correlation between time passing on and them getting better. The fish hat is clearly irrelevant. Their immune system is acting. They're resting, which is a good thing to do when you're not feeling well, to allow your immune system to work. They're eating. There could be placebo effects too. So correlation, causation. I was sick. I did X. I got better. So what? It could have been the fish hat. Could have been the rest. Could have been something else. If you're motivated to believe in something because you just spent $20 on some remedy, yeah, it becomes this unscientific anecdote. You go around telling everyone what you think happened, but we can't run research designs that way. To talk about the other research designs, I need to now define independent and dependent variables. And it's not as hard as it sounds. The dependent variable is the behavior of interest. It's what you're measuring. You're measuring the dependent variable, sometimes called a DV. The independent variable is the hypothesized cause. And that's what ideally, you can't always do this, but ideally you manipulate the independent variable, okay? And I've got various shapes for them then, which I'll keep consistent to hopefully help you understand. So let's think about this independent variable, the amount of noise while you're studying. And this one's got 3 levels. We might refer to them as levels of the independent variable. No noise, quiet noise, loud noise. Levels of the independent variable. Now, you might call one of them a control condition. That's where control condition comes into it. It doesn't matter. There doesn't always need to be a zero noise control condition. It's enough for a good research design often to just manipulate levels of the independent variable, but I just thought I'd mention it there. Here's another one, another independent variable. Online lectures watched. Did you watch none of the online lectures? Did you watch 50% of them? Did you watch 80% or more? Those would be levels of that independent variable. But are they manipulated? Can you actually force someone not to watch any lessons for a course they paid for? Can you force them to watch 50%? Can you force them to watch 80%? If you can't, and there is no manipulation, then it's something I've already talked about. It's a correlational study, okay? You're just measuring how much they've watched. In fact, do I change the shape? Yes, I change the shape because these are essentially dependent variables. And if you're just measuring them, you're relating, you're associating, you're correlating the amount of lectures watched with the ultimate dependent variable of exam performance. And that's a correlational study. There is no manipulation. There is no control. And the problem when you have no control is there's so many different alternate explanations. The obvious one here is that lecture watching might be useless. It might not be what's directly causing exam performance. It might simply be that a student is motivated to watch lots of lessons and they're also motivated to study. Ultimately, they do well in the exam. Okay, something else is causing X and Y, even though X and Y are correlated. And that's the problem when you have no control. Let's imagine that you manipulate the online lectures watched though. This is, I don't think I'm going to go with the online lectures watch because that seems a bit implausible, but when you manipulate the independent variable, what that means is you're deciding who is in each condition. You're forcing them to do certain things, right? You're in condition 1, you're going to do this. Condition 2, you're going to do this. Condition 3, you're going to do this. When you do a research report study in psychology, almost always the computer has allocated you to a condition that you're not even aware of, but you're asked to do a task in a certain way without even knowing that. You're blinded to it. Whenever it's the case that you're put into a condition at random, that's called random allocation. Random allocation is a very important concept in research design. I've got someone tossing a coin there. People turn up to the study, and it's usually not someone tossing a coin or rolling a dice. It's usually a computer which is saying, this participant's going to be in the no noise condition, this participant's going to be in the quiet noise, this participant's going to be in the loud noise condition. That's random allocation. People arrive at the study not in a condition. People are never given the option to choose a condition. People are put into a condition. So whatever pre-existing differences they have that might differ amongst them, they're going to balance out because your sample is going to be spread evenly across the 3 conditions. So for random allocation to occur, the researcher is able to control who's in each condition, and the condition participants are in is randomized. It's not random allocation, and I've mentioned this already, if participants choose their condition, or if participants arrive at a study already in a condition, which sounds odd, but I'll explain that in a moment. Who's already in a condition? Well, we can't randomly allocate all these things that just popped up. Sexuality. Oh, thank you for signing up for my study on sexuality. Toss a coin. Heads. Okay, you're going to identify as gay for the next 30 minutes. Piss off. Okay. Toss a coin. Okay, oh, you're going to be a standard heterosexual person for the next 30. No, you can't do that. Look through all these variables. You can't randomly allocate these things. And yet, sadly, these are the things that psychologists are often interested in the most. Intelligence, morality, study habits, lecture viewing. I can't do that. There's a third-year lecturer who has always requested that we randomly allocate you to the amount of lectures you watch. It's completely impractical. Brain damage, not going to happen. Random allocation is difficult in these situations. It's impractical, it's unethical, it's expensive. That's just for the ones that are yellow. The ones that are still in white, it's basically impossible to randomly allocate. If you're wondering why brain damage is in yellow, there is a new technique called TMS, which uses powerful magnets, which is, in a sense, is a kind of temporary brain damage. You can try and find a study on that on Sonar, if you're curious. This is a problem for psychology if we can't randomly allocate a lot of variables. So let's go back to the variables. Our independent variable is the hypothesized cause. It's manipulated, or you get people in pre-existing groups. And DV, dependent measure, you're just measuring it. Let's go through the remaining research designs then. I already mentioned correlational study, but I'm going to put that now in the context of how many of the independent variables of interest are randomly allocated. You know what independent variables are now. You know what random allocation is, the ability to put people in different conditions. To work out which one of these kinds of study a study is, we simply ask this question. If the answer is all of the independent variables of interest are randomly allocated, it's a true experiment. At least one, but not others, quasi-experiment. Quasi sounds fancy, not quite an experiment is what that means. Something can't be randomly allocated, something can be randomly allocated. Correlational study, none. Nothing's randomly allocated. Everything is simply measured. Nothing is manipulated. It's as simple as that. I'll give an example, but it is as simple as that. So let's say, for example, we want to do a true experiment on do violent video games and caffeine cause aggression. To be a true experiment, we need to be able to randomly allocate and manipulate the levels of violent video games played. So I've got there a none condition and a 1 hour condition, and the amount of caffeine consumed. So to make that practical and work as a study, oh, thanks for signing up for my research, toss a coin, get a computer to pick, right, I don't know, you're going to play something awesome like Stardew Valley, which is not, is it violent? No, it is in the caves. You're going to do a farming game that doesn't involve violence, which is none, or you're going to play Doom or Fortnite or something like that for an hour, something violent. So you're actually going to tell people to do one of these things. And you're going to tell them, toss a coin, oh, okay, you're just going to have water, or, oh, you're going to have water with caffeine in it. Complete control, complete random allocation of independent variables. And then you're going to measure their aggression as a dependent measure. For a true experiment, if you have control over all these things, you can draw a very strong causal inference. There's none of that guessing with correlational studies. If you randomly allocate these things and it turns out that people who drink more caffeine are more aggressive, or who play the violent video games are more aggressive, that's a really powerful causal inference you can draw, that these things are actually causing the aggression. Imagine though, even though we can easily randomly allocate caffeine, we're not going to bring some violent video game into the laboratory and make people play it for an hour. We're just going to ask them in a questionnaire, how many violent video games have you played? None, some, many. We're not manipulating that independent variable of interest. We're just measuring it. Suddenly our experiment becomes a quasi-experiment. It's not a correlational study yet though, because we can still manipulate caffeine intake for that particular time period. Other explanations here cannot be ruled out. You'll see in the bottom right there. Like, well, you know what? People who are aggressive anyway might enjoy playing aggressive games. So if they say many and they end up being aggressive, that might just be because they're aggressive people. See the problem? The moment you lose control, the moment you lose the ability to randomly allocate, you lose the strength of your causal inference. So quasi often isn't that great. It is a bit better than a correlational study though, where no independent variables are randomly allocated. You're asking them how much caffeine they've drunk. You're letting that vary randomly too. And you're asking them how many violent video games they've played. You're just measuring everything basically. And now you've got the problem where they arrive at the study being a caffeine drinker or not, and that may relate to aggression also. You just don't know. So that's an example, but it does really just boil down to that one question. How many independent variables of interest are randomly allocated? The causal inference you can draw is usually very strong for a true experiment, moderate for a quasi, and very weak for a correlational study, unless you can spend a lot of time and effort ruling out the many alternative explanations. Notice that I've got something called internal validity, which is also strong, moderate, and weak, and that's because the meaning of internal validity is just the extent to which you can draw a strong causal inference. Strong causal inference can be drawn, strong internal validity. Weak causal inference only can be drawn, you have weak internal validity. I think I've got a definition coming up. Yep. Internal validity, pardon me, how certain we are that changes in the independent variable are caused by changes in the dependent variable. Strength of the causal inference, basically. Now that's very different to external validity, which is simply the extent to which our results can be generalized to the wider population. That's something that has more to do, not so much with the causal inference, it has to do with how representative the sample is. How realistic was the study? For example, playing a violent video game for an hour, does that really compare to playing violent video games for hours every day for a lifetime? External validity does what you found in the lab, does it generalize to the outside world? Lab situations tend to be more artificial. They tend to be more constrained in what you can and can't do for ethical reasons. Does what we find in a lab generalize to the outside? Well, now I have to say, and again, Dr. Rebecca Pincus will lecture you in social psychology, not all psychology experiments which are highly controlled have, pardon me, low external validity. Social psychology has some great experiments which almost exist in entirely naturalistic settings, but where, thanks to the fact that you have confederates or other people who are basically actors, they feel completely natural to the participant. They don't feel artificial at all. So random allocation is placing participants in conditions at random. And using what you know about random allocation, you can decide whether or not a study is a true experiment, a quasi-experiment, or a correlational study. I haven't mentioned random selection. This is the first time I'm mentioning random selection. So this is something really important. You need to put a big red line in your notes and say to yourself, you know what? Caleb wrapped up talking about deciding whether a study is a true experiment, a quasi-experiment, or a correlational study before he even mentioned random selection. So that should tell you that random selection has nothing to do with the type of research design, and it doesn't. How many of the independent variables are randomly allocated? Yep, that's the number one way to distinguish between them. How are the participants selected? Random or not? And it's rare for me to use such a radical color such as purple on my slides. It does not friggin' matter. And yet, over the years, the number of multiple choice questions in final exams and exams I've made, which just replace the word allocation with selection, because I know that hundreds, thousands, tens of thousands of students across the years, allocation, selection, random, it's got the word random, and they're not even reading the word after that. Random selection, it's good for external validity, random selection, you want a nice representative sample, good for external validity. Does it relate at all to what kind of research design you're talking about? No, it does not matter, so watch out for that in your upcoming exams. Replication, just a few more loose ends to tie up. Replication is when you repeat the study in the same manner and you, find the same results. You hope to find the same results. You hope to replicate the study. This is why method sections in journals are so thorough, because you're explaining how the study was done, and then someone on the other side of the world can repeat the study and with any luck replicate what you found. It doesn't always happen. It's critical in science. Dr. Rebecca Pincus, once more, I'll refer to her, I think this is the last time. In social psychology lectures, she will talk about something called the replication crisis in psychology, where we've got some amazing experiments in social psychology, but people have had a lot of trouble replicating them. But it is important. Before I move on, because if you believe that, I don't know, what's something silly, like echinacea cures the common cold or something, that's not true, by the way, if you look into it. But if you believe something like that and you're just looking around for confirming evidence, you probably will find one or two studies which show that. But they won't have been replicated. So be careful of cherry picking and confirmation bias. Replication is more important, being able to find the same thing over and over again when it's repeated. Very important in science. Okay, blinding. Blinding is when participants are unaware of what condition they're in, and also when researchers are unaware of which condition is being run. There's several kinds of bias that result. If you're a participant and you've guessed what condition you're in, and this is the unspoken goal of every psychology student, to always try and work out what the study is about while you're doing it, that's okay, everyone does it. But if you manage to guess that, then you might have placebo effects. You might get better, even though nothing's been given to you. Or nocebo effects, that's kind of the opposite. We see that a lot with vaccine side effects. Most of them are thought to be nocebo effects. People are expecting to feel bad. They feel bad, they blame it on the vaccine they've had, but it's actually nothing more than a nocebo. Or just other biases. You can really spoil an experiment if you've guessed what condition you're in. So best to be blind to it. Best to not know that this is what the expectation is, what the hypothesis might be. Researchers too should be unaware of the condition they're testing. And that's why it's better to use a computer to do your random allocation for you. Because if you know, for example, that this participant is in the condition that you're hoping is the faster condition, you might be encouraging them. And the way you apply the condition, the way you give them the tasks might be faster. Even if it's done unconsciously, researcher bias can be unconscious. And when you're coding the data, even if it's good qualitative research, if you know what condition they were in, then you might have unconscious measurement bias or fully conscious measurement bias. If you're blinded to both, if participants are blind and researchers are blind, then that's called double blind, and that's the gold standard for research designs where you've got multiple conditions. Now, I've covered a lot there. It's fairly technical. You've got to learn the terminology. You've got to be able to do certain things. There's a whole tutorial based just on this lesson, the research designs tutorial, which will give you more practice. And I'll give you a lot of practice in the upcoming workshop also. But there's even more you can do. Now that you're a psychology student, you can start reading about research that you're interested in. Don't wait for a lecturer to mention something you're interested in. Learn how to use databases, learn how to use PsycInfo, off you go. Find something you're interested in, and next time you're reading a paper, identify the independent and dependent variables. What are they manipulating? What do they think is the cause? And what are they measuring? What's the dependent measure? Consider the internal and external validity of the research you're reading about. How strong are the causal inferences that are being made, internal validity? How generalizable are these findings to the wider community, external validity? And this is the ultimate, this is, I think, towards the end of the tutorial. Create different examples of research with your study group and swap with your study group. And then challenge each other to classify them as true, quasi, or correlational. Do what I do when I'm making exams and switch up random selection with random allocation. See if they notice. See if they realize that one is incredibly important, random allocation, and one doesn't matter at all, random selection. See if they notice. Do that, you'll know things upside down, you'll know things backwards. And that's the end of the research designs lesson. So get practicing, and I'll see you in the workshop.